Okay, so hello and welcome to this video tutorial for this simple mass balance problem that we have here. Um, Before we get into tackling this problem, I figured it was worth going over a little bit of theory in relation to mass balance. 2 points. The first one is what do we kind of mean by a mass balance? Well, a mass balance is kind of a term we use to describe kind of a calculation that you might use to determine the mass of a particular species going in and out of a chemical system. It's described with this kind of idea that accumulation is equal to what goes in minus what comes out plus what's generated in the system and what's consumed in the system. In the context of this problem, and in the context of the kind of simplest mass balance problems that you can come across, there is nothing accumulated in the system here, and also there's no reactions going on inside our system, so we can't say that there's anything being generated or consumed in the system. So we have this 0 equals in minus out left over, or we could just say in equals out, right? The mass that I put in is equal to the mass that I get out of a particular thing. The second point I wanted to cover is this idea of degrees of freedom. So degrees of freedom analysis is something that is very helpful for tackling mass balance problems, particularly maybe as they become more and more complicated. We understand that degrees of freedom in this context, it means the number of unknowns, minus the number of independent balances that we have, minus any other relations that we have. If I have a positive number of degrees of freedom or a greater than 0 number of degrees of freedom, that essentially means that the problem is underspecified and isn't solvable yet. It might mean then that you need to define one of your unknowns, or that you need to define a relation, which will then help you bring your degrees of freedom down to 0. And once you have the 0 degrees of freedom, that is suggesting to you that the problem is, in a sense, perfectly specified, or specified enough such that you can solve the problem. Okay, the problem is solvable when you have 0 degrees of freedom. Negative degrees of freedom is something that you might rarely encounter. It may mean that the problem is kind of overspecified, or that we know too much, or too many values are known, or that too many equations are known. So that's what we mean by degrees of freedom. Degrees of freedom analysis is where you might start, really, with pretty much any mass balance problem. I would suggest starting with the degrees of freedom analysis here. So we could say that we have 1, 2, 3 unknowns here, right? M1, M2, and M3. How many independent balances do we have? Well, we have a balance for A and we have a balance for B. So we have 3 unknowns. We can say degrees of freedom in the context of this problem is 3 unknowns minus 2 independent relations, which is equal to 1. The problem is underspecified. Okay, let's look at what the question's actually asking here. It says determine the mass proportion of species A that enters the mixer via stream 1 for the following system, where we have this diagram here. So the question's basically asking, of the A that enters the system, how much of it enters via stream 1 or M1? One way we could determine that, or one way we could express that, is 0.3 M3. That's describing the A leaving the system. And since we understand that in equals out, well, the A kind of leaving the system is equal to the A entering the system. And we're asking, of that, how much is entering via stream 1? Well, we could express that A entering via stream 1 as 0.2 M1, right? So this is what we need to determine here. We have a positive number of degrees of freedom, so our problem is underspecified, but we note that the most important thing about this problem really isn't the values that M1, M2, and M3 are taking. It's the proportion that they have to each other. So one way to solve this problem might just be to assign a value, a nice neat value, to one of our unknowns here. So let's just say M1 equals 100. That's a nice, neat number. So let's go ahead and do our balances then. We can say for A that 20 plus 20 being 0.2 times 100 plus 0.45 M2 is equal to 0.3 M3. For B, we can say that 80 plus 0.55 M2 is equal to 0.7 M3. Now, evidently, this is just kind of a system of linear equations here. One way we can solve for M2 and M3 is using the elimination method, which I'm going to trust you guys are familiar with already. So I could label this equation, equation 1, and this equation, equation 2. I'm going to divide equation 1 by 0.3, and I'm going to divide equation 2 by 0.7. In doing that, the coefficient of M3 will become 1 for equation 1, and the coefficient for M3 will become 1 as well for equation 2, which will then allow us to eliminate M3 from our system of equations here. So I could say equation 1 divided by 0.3. What does that look like? Well, it's going to be 20 over 0.3 plus 0.45 over 0.3 M2. And that's all equal to M3. Equation 2 divided by 0.7, that's going to give us 80 over 0.7 plus 0.55 over 0.7 M2. And that's, again, all equal to M3. Right. Since this is equal to M3, and this is equal to M3, we can equate them to each other. I could say that 20 over 0.3 I could say this effectively, and when I subtract this, no, wrong way round, when I subtract this from both sides, and when I subtract this from both sides, what I'll land on is something that looks like this, where I have minus 47.62 is equal to minus 5/7 of M2. I can then rearrange that. I can say, therefore, M2 is equal to 7/5 of 47.62. Which is equal to 66.67. Now I could take that value of 66.67 and I could then substitute it into my equations here. I could substitute it into equation 1 or equation 2. But I don't need to do that. The reason I don't necessarily need to do that is because when I refer back to my diagram I have here, I note that M1 equals 100, M2 equals 66.67. Therefore, M3 must be the sum of those two. So I can say M3 is equal to 166.67. Okay. Now, since what we noted earlier that we're looking for this 0.2 M1 over 0.3 M3 idea, we can substitute those values in. We can say this is 0.2 times 100 over 0.3 times 166.67, and this is all equal to 40%. Okay, so we land on 40%. This was quite taxing, or this was quite a kind of laborious problem that we did here that involved lots of mathematical technique. One thing that I like to emphasize to my students is that it's okay, actually, as an engineer, to kind of outsource that kind of cognitive or that kind of mathematical load to maybe you have a mathematician in your team. as an engineer, or maybe you can outsource it to an online tool. So what I've done here is I've written out the exact same equations that we just solved in that problem just now, and I put them into Simulab. I could have put them into various other tools, right? But it's given me the values for M2 and M3 like that. So this is why I emphasize to students that, you're engineers, not mathematicians. It's okay to make use of these tools. You are saving yourself energy, you are saving yourself time by doing this. So this is a perfectly valid approach to solving this problem, is to outsource that to kind of an online tool. Okay, so if you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.